Yes, yes. So let me share my screen. Is it visible?
Yes, yes.
Okay. So welcome back. So today what we are going to discuss is RNN and LSTM. So till now what we have discussed how to process a text using neural network, and we have also seen how to represent the text for creating a vector using what to vec models. Okay. So till now what we have discussed, that in order to process any text, what we need, if you are using a deep learning model or neural network, your first job is to convert the documents into vector form. Now, initially, we have discussed how to convert the document into vector, and the BOW, bag of word, different types of bag of word models are there. So we are using these bag of word models to convert the document into vectors. These vectors are given as input to the neural network, and whatever is the architecture of the neural network, it will decide and find out the output. But when we say that we are representing the document in a bag of word concept, basically bag of word can only capture the word present or not in a particular document. If it is present, the value will be 1. If it is not present, the value will be 0. Even if you are using a TF-IDF, uh, mm, TF-IDF method for converting the document into vector, still only those positions of the word will be converted into some numerical form. Instead of 1 and 0, there will be some real numbers, but rest of the positions are 0. Another aspect of this document vector using bag of word or TF-IDF is that the size of the vector is depends on the number of vocabulary in that corpus. Now, if the corpus is very big, that means your most of the data in that vector will be 0, so it creates a sparse representation. This is one problem. Another problem with this kind of representation is that it cannot capture any kind of meaning of the document. Only it captures whether a word is present in the document or not. So that's why we move further to for the representation part, that how we can represent. Now we use a static representation, or we call it as static embedding. How static embedding is being convert is used. So one example of static embedding is your word to vec, and we have already discussed here the document is not converted into a vector. Here the word present in that document, for every word we represent the word in a dense vector. So the sparse, it is not sparse, rather it is a dense vector. And not only that, this dense vector captures some kind of related meaning of words. And once we have the vectors for every word in that document, let's say D1 is the document, and the D1 contains three words: dog bites man. For every word, it is converted into some d-dimensional vector, and which is a dense vector, not sparse vector, and the size of the vector is very limited. It is up to between 10 to 500 or 300, whatever you take. And once you convert each word into vector, then these words, these word vector will be averaged. Sorry, these word vectors will be averaged, and one final averaged vector will be created for these word vector. This averaged vector is representing the document, and that average vector is feeding to the neural network to produce some kind of output. So here in static embedding, it captures some relative word meaning. But one problem with, and it is very good for the base models, but one problem with static embedding is that it throw away the word order, because we know that word order is very important to understand the meaning of the whole sentence. How? Let's see. For example, this sentence here I have represented three sentences. One is I was late for work, I was late for work because I missed the bus. Now if you see this, the meaning of the sentence is more clear if you have a more number of words. I was late, it's okay, but I was late forward means you are adding two other words which will give you more clarity that why you are late. And I was late for because I missed the bus. So why you are late? Because I missed the bus. Now you see, in order to understand a sentence, how human beings are actually understanding this sentence, how we are understanding the sentence, how we are processing in a sequential order, one after another word we are reading, and once we get to the end of the sentence, then we are inferring some meaning out of that. Okay, that means in order to properly process the sentence or find out the proper meaning of the sentence must be processed sequentially one after another. Means words will be processed one after another. It's not a kind of a bag of words. It's not that you take bunch of words and process it. In that case, the word order will be missing, and it cannot capture the real meaning of the sentence. Even if it can capture the meaning of the word, but the meaning of the word will differ when it is present in with other words. Okay, this is number one problem. That word order is not considered in the approaches which we have discussed previously, and that's why we are not getting appropriate meaning of the sentence. Number two, that when we are using a neural network, the neural network input layer is fixed. That means if you create a neural network with 50 let's say dimension, means 50 input units, that means whenever you are going to process it, you have to convert your document into a vector of 50 dimension, number one. But if you want to process it sequentially one after another the words, and if you try to convert each word into vector and feed these words, then problem is that every sentence is not of same length. Means in every sentence number of word may vary. So it is very difficult to create a neural network which will take different number of inputs at different times. Okay, so this the text sequences vary in length. That is another problem which we cannot process through your neural network. And let's take another example. Let's say dog bites man, man bites dog. Now, if you use these two sentences, if you are using BOW, means bag of word, so same three words is being used in both the sentences, and their representation, as we are not considering the order of the word in which order they are appearing, we are considering it's a kind of a bag of words. So what will happen? Now, the representation of for both the document will be same. Now, if it is same, then the meaning cannot be different. Okay, so the question is here that in order to understand the meaning of the whole sentence, you need to process them sequentially one after another. That means word order matters, because dog bites man, man bites dog is totally different. Meaning is different. Okay, let's take another example. Let's say I'm giving this sentence that when you read the sentence, the dog looked guilty. So when you read the sentence and understand the meaning, it will create some kind of funny picture in your mind. Okay, and if you see another sentence, the defendant looked guilty. So it is very same. It is not that much amusing, because dog looked guilty. So dog cannot be guilty. Okay, but defendant means he is doing sometimes means some person has done something bad. So the defendant looked guilty. Okay, so that creates another picture. That means the looked guilty, the looked guilty will give you some picture. So the looked guilty depends on the previous word, your dog and dependent. That means once only one word is changed within the two sentences, only one word change creates a different picture in your mind, means their meaning is different. So here what we are saying, that the meaning of a particular sentence depends, or the meaning of a particular word you can say depends on its surrounding words, or how this word is appearing with other words. So this is called the context. So that means to better capture this kind of context, we can process sentences as sequences. So here three things we have noticed. One is that the word order matters in order to understand the total meaning of the sentence. Number two, variable length input is required, because the sentence length is not same for every word. Number three, that the words depend on its surrounding words. We call them as a context. So to understand the meaning of a particular word in more appropriate way, we need to understand the context of these words. So to represent or to solve these three problems, your sentence or document should be processed sequentially one after another, word by word from left to right. Okay, so to do that, what we need? We need a different kinds of neural network. That is called a recurrent neural network. Let's see what is it. So let's say I have just simplified the neural network. Let's think this is a neural network. Here input layer is there, X is input. It may have some dimension. Okay, and whatever is the dimension, that many input units will be there. There is one hidden layer, and a hidden layer, the dimension here I have not mentioned. Some dimension is there in hidden layer, and after that one output layer is there, and it produces some output y cap. Okay, so if I want to process, and this is the neural network, I am just simplified it and put in a one line. Actually this is not one line, the lines are not one, there are many connections, because the input unit X contains many input units. Hidden layer have many neurons, output layer has one, or depending on your task it can have one or more output layer neurons, and they are connected, densely connected. But to represent in a simple way, I am putting this as a one line. Okay, so imagine it is a neural network with one input layer, one hidden layer, and one output layer. Okay, and the hidden layer is represented at H, a input layer is represented by X, output is Y cap. Okay, now if I want to process this sentence, the dog looked guilty. Now I am saying that the it will be processed sequentially one after another. So even if you are using a simple neural network, okay, now what you will do? You will convert the first word the into its corresponding vector form. Let's say it is a 8 length vector. Okay, so the if it is 8 length vector, you feed it in the input layer, and it will be processed and it will give you some output. Okay, but when you go for the second input, let's say that is the dog. So when you input dog, the dog will be independently inputted. Means the vector of dog is given as input to the X, and it is processed independently. That means every word, if you want to use simple neural network, every word when you feed it to the network, they will be processed independently. Well, then what is the problem? If it is independently processed, that means the word which is dependent on the previous word, that relationship cannot be captured. Means dog is processed independently, it gives some output. Dog is processed independently, because dog before this the word is the. Looked before the word is the dog, and guilty before three words are there, the dog looked. So when you process guilty in a simple neural network, these three things are not there. Only guilty is processed independently. That means the word order is missing. Means the context is also missing. Even if you execute the neural network and feeding these embeddings one after another, as they are not dependent, means there is nothing called memory. Because if there was a memory here, then the memory can contain the information of the dog and looked when it is processed guilty. So simultaneously it can process all of them. And as there is nothing called memory, so it cannot capture all these information of these previous words when you are processing guilty. So to solve this, what the change we need, just to add a recurrent connection to the hidden layer. What does it mean? It means that it is the same simple neural network, but here hidden layer, within the hidden layer, there is a recurrent connection. Means the hidden layer now is not getting only one input, that is the X. Rather, it also get the input in the next word when you process, that the previous word's output. So here the hidden layer receives two inputs. One is current input X, and the output of the hidden layer from the previous time step. Okay, try to understand. So so to represent this in more clear, let's put the some of the notations. So here xt, ht, yt, these are the input, hidden state output, and the output, final output. They are present in time step t, and at the time step t, the previous time steps output of the hidden layer, that is ht minus 1, is given as input along with the current time steps input xt. Okay. Now if you unroll it through time, just you see this is only one network, there is only a recurrent connection. But when you unroll it, means you just imagine that every time step how it is processed. So at a time step means at first time do is processed, second time dog is processed, third time looked is processed, and the fourth time guilty is processed. Means at every time one word is given as input to this neural network. But as there is a recurrent connection, how actually it is processing. So here when time step t equal to 1, so the do is given as input. Okay. And in time step 2, dog is given as input. So when dog is given as input, the output of this previous time step from the hidden state ht minus 1 means ht equal to 1. So here the time step is 2, the previous time step already it is calculated, you got its output as ht minus ht equal to 1, that is also given as input to the current time step, that is t equal to 2. So along in the second time step, not only it takes only dog but also the hidden state output of the previous time step, and here the hidden state output contains the information of dog. That means when it is processing dog, it is not processing independently the dog, rather it processes dog along with the previous words information which is captured in the hidden state ht equal to 1. Now it produces some output, and similarly when looked is processed, then what it will do? So at the time step 3, looked is given as input, and the ht equal to 2, it contains the information of both the previous input, that is do and dog, because do information is passed through ht equal to 1, and now dog information is added here. Now do and dog information is there, and it is passed through ht equal to 2 to current time step 3. Now, when it processed looked, it does not process looked as a single word, rather it is processing looked along with the previous information which is captured by ht equal to 2. And like this it process, and you got at every time step you can get one output. Okay. So at time step 2, this is my generated output, that is the information from the dog. So the is there, dog is there, both information will be used, and it will give you the output, some output here. And similarly when it is time step 3, looked is there, and similarly at time step 4, guilty will be used. And here when guilty is processed, it uses all the information, that is the dog and looked. Where this information is present, these three information is present through this ht equal to 3, because ht equal to 3 contains what? The dog and looked. These three information is passed to ht4, and guilty is passed. Now guilty is not processed alone, rather all three other words information is there, and it is processed, and it will give you a good result. Okay. So generated from the whole sequence. So this is called your recurrent neural network, because there is a recurrent connection between the hidden layer. That means previous output of hidden layer is given as input to the current input along with the current input. Okay. So if you see mathematically how it is doing, now between xt and st, this is input layer, this is your hidden layer, and there is a set of weights present between xt and st. Let's call it as u. So U is a hidden layer matrix which contains all the parameters or weights between xt and st. Okay. And similarly V is another set of matrix or another set of weights which is present between st and output yt cap. Similarly between st and st minus 1, so what will be the output, that we'll see. So you see generally what happens now, how yt cap is calculated. Now there is a some output function here, some activation function g with v into ht. So v into ht passed through some activation function, it will give you output yt. But what is your ht? How ht will be calculated? So your ht will be using not only xt but also ht minus 1. In order to calculate ht, we need xt current input and the hidden states previous hidden states output, and the parameter or the weights are also there between ht and ht minus 1, that is called a w. W is another matrix. So what is your HT? So your HT is nothing but a function where U into XT plus W into HT minus 1. Some bias is there. Just for the simplicity, we have not put the bias. So bias is there. Plus B or C, whatever is there. Okay. Now, this is your HT. HT is given to this function G with V as the parameter set, and you get the output. So this is the mathematical equation for a recurrent neural network. Okay, what is it? Now here, what are the parameters? Parameters or weights are nothing but U, V and W. U is between XT and ST. W is between HT and ST minus 1, means previous hidden state and hidden state. And between hidden state and output state, V is the vector or V is the matrix. Okay. Now, when you unroll it, actually we are using only one neural network with recurrent connection. That means at every time step, same UWV are used. In same set of weights are being used at every time step because it is a one network. Only there is a recurrent connection. So that's why number of parameter here is less. Okay, because same set of parameter is being used and it is being trained. Okay, so this is called the unrolled version of this neural of this RNN. Okay, and for simplicity, let's call the hidden state as a cell. So here in hidden state, we are assuming that only one hidden layer is there. That can be many hidden layers, or that can be any other architecture or other kind of architecture can be present also. That's why, well, let's call it as a cell. So cell is either one hidden layer, or it means it can hold any other kind of neural network architecture. Okay. So the question is here, what will be HT0? Now for this time step, let's say for a time step 2, the previous hidden state output will be given as input, that is HT1, and current input is HT2. But when it starts at the beginning, so at time step 1, instead that is at time step 0, we are using a 0 vector. So generally a 0 vector is being used. So that it will sit in different way. Output you can use at every time step the outputs, or you can use only one output at the last time step, ignoring the other output in different time steps. Okay, and to sequence problem. For example, if you are going to do a POS tagging, the problem is a sentence is given, that is the dog looked guilty, part of speech, whether it is a noun, verb, or adjective or a determiner. Okay. Yes, there is a question. What is the question? Will the weights not change as we unroll? No, no. You see, just you imagine it is a rolled thing. Okay. That means this is only one network. At a different time, we are feeding one word. And as there is a recurrent connection, so the previous information is not lost. Rather, previous information is given as it's a kind of feedback loop. So previous information is given as input to this current time step. And as it is only one network, so the weight will only change. It does not mean that at this time step some weight will be there, at this time step some weight will be there. No, the UWB will be uniform across all time step. Is it okay, Anurag? Okay, so that means at every time step, same weight is used because it's a network. Just to understand, for our understanding purpose, we are just unrolling it. Actually, it is a one network. There is a connection here. Okay, so this is the case. So now the question is, in which kind of problem we can solve using this RNN? One is some sequence to sequence problem can be solved. What is sequence to sequence problem? One problem is very simple, that is part of speech tagging. Another one can be a named entity recognition. It's a little bit different than this one. We'll discuss. So here, for every word, we have to output one corresponding part of speech. Okay, so for that, this RNN is very one. The is given as input, so it process, output will be created. Now, as there can be many, it's not a binary because there can be many possible output. So we have to use a softmax and it produces a determiner. In the second time step, you give dog, and the dog, in order to properly find out what will be the POS or part of speech for dog, we need to understand what is the previous word. So the previous word information is currently coming through this recurrence connection. Now the processing dog along with the information of the, and this will be again produced noun, and similarly it is going to produce all the corresponding part of speech outputs. Okay. Another is that instead of collecting each time step one output, will ignore all these outputs, rather will only concentrate on the final output. Like for classification, you can use RNN. So in classification, whether it is positive or negative, okay, a sentiment classification. So what you will do, you create word vectors like this using any word to hack or any model, pass this to this RNN, and don't collect the output at every time step, rather you collect the final output. So final output, whatever is this hidden state representation, that hidden state representation will be used to a, if it is a binary, you use here sigmoid, and one output will be produced. If it is a multi-class classification, you use softmax here. So one of many output will be produced. And why this is important? Because this ht equal to 4, it does not contain only the information of guilty, rather it contains all the information of previous words. That means I can say ht equal to 4 is the representation of the entire sentence. Now entire sentence is represented by this, so you can add a softmax or sigmoid depending on the type of classification, so it can classify. So this is also can be done. Okay, and there are also many other varieties of RNNs are there. Now let's see how the vectors, or these, when we say that these UWB, these are the parameters or weights, how these weights are trained. Okay, so here the training process is called back propagation through time. In previous RNA, in the neural letter, we say only back propagation, but here it is back propagation through time, because at a different time, different output is produced, and we have to go through the previous time steps in order to fully update all the values of U, W, and V. Okay, so now you see at time step 0, the hidden state of ht0 is all are 0, is a 0 vector, and the current input is given, and a hidden state representation will be created, and then it is output as yt equal to 1. At the next time step, the output of ht equal to 1 will be given as input, as well as xt equal to 2 is given as input, and it will produce output, and like this it will continue. Now in order to find out the output at every time step, we in order to find out the loss, what we'll do, we have to calculate loss at every time step. Okay, so at a time step 1, whatever, let's say it is a, what part of speech tagging problem. So at a part of speech tagging problem, at each time step it is producing one output, but at that time step, whatever is the actual output that is there, now you use the predicted output and the actual output and create a loss function. Now this is loss function LT equal to 1. Let's say it is categorical cross entropy. If it is a multi-class classification problem, so we are using categorical cross entropy, and at t equal to 1, we will get the loss. Okay, now as we get the loss at time step t equal to 1, now we move to the next time step. So next time step, it is going to produce another output, and corresponding to this input, and its original output is there. Now using this original output and this predicted output, we calculate another loss at time step 2, and similarly for every time step you got one predicted output, it this corresponding actual output at that time step is there. Use this actual output and the predicted output and calculate loss using any loss function, and as it is a classification, so we can use categorical cross entropy loss. Now you got a 4 loss at a 4 time steps at different time. These are the losses. Now to find out the total loss, what you can do, you can add them and divide it by number of time steps. So total loss is just add all losses at all time step and divide it by number of times. So now you got the final loss function for the whole network. Okay, once you get it, what you will do, You just in the same way you just calculate the gradients, like the previous back propagation method we have discussed. So just calculate the gradients loss with respect to v, because we have to update v, u and w. Okay, we have to update v, u and w. So that means the gradient to be calculated with respect to v, with respect to w, and with respect to u. So you just calculate the gradient. Then once the gradient values are there, then you can update the u, v, w using the updation. Sorry, your stochastic gradient descent updation. What is that? And the new v, w or u equal to old v, w and u minus some learning rate into the gradient of the corresponding u, v and w. Okay, and you use that. Now question is how you will calculate these vectors, sorry, these derivatives, partial derivatives, because at different time step it is unrolling. That means at particular time step t equal to 4, these things are already passed. So how we'll do that? Now we have to find out how we can calculate the derivative with respect to v, derivative with respect to w and u. Let's see. We'll not calculate in detail, rather for your simple understanding I am just discussing something. Okay, so here how to calculate del L by V? So del L is loss is there. Now del L by V. So what will do? You just calculate this with respect to all time step. So at time step t L sorry 4, you calculate del L by V. At time step t equal to 3, you calculate del L by V, and like this. Then all will be added. You will get the final del L by V. That is summation of t equal to 1 to t del L t by del V. So this is very simple. That means L is dependent on V, so you directly can calculate. Okay, so it's not problem, not that much problem. So at every time step, you calculate the partial derivative and add them, just it. But how to so how to calculate individual del LT by V? Because you know that del LT by V depends on YT, loss is depending on Y is dependent on the intermediate output Q, and Q is dependent on V, like we have already done in the previous RNA, sorry, in previous neural network case. So just apply the chain rule, multiply it, you will get what is QT. QT is nothing but V of HT. We know that this QT is V of HT. So use this in your derivative calculation and you can calculate it. It's very simple. It's not that much difficult. But imagine how we'll calculate del L by W. So del L by W is exactly same. What you do? At every time step, you calculate loss with respect to W, add them. This will be del L by W. But in each time step, how you will calculate W? That is the problem. So here you see, in order to calculate del LT by del W, what we'll do? First, we have to calculate del L by del Y, then del Y by del Q, then del QT by del HT. Okay, and then del HT by del W. So del L by del Y, del Y by del Q, like before, del Q by del HT, del HT by del W. Okay, now this is what time step 4 I am calculating. So at time step 4 del HT by del W. But imagine or just see del HT by del W you directly cannot calculate, because this W is depending on previous HT. You know it. So now what you'll do? So now concentrate on this part. Del HT by del W. It is not straightforward, because this del HT depends on previous HT. That HT is again depends on previous HT. So there is also W is available. So what you do? We have to calculate del HT by del W. How you will calculate? Now like this. Del HT by del W for this time step. Now it will go one step further. Now that HT is depending on this HT. So here del HT by del HT minus 1. If it is whatever may be the HT equal to 4 means this will be HT 3 by sorry into del HT minus 1 by del W. Now this W is again depending on the previous HT and W. So again you have to calculate this one, del HT minus 1 by del W. Again it will be del HT by del HT minus 1, HT minus 1 by HT minus 2, again HT minus 2 by HT W. Like this you will go back. As here to calculate the derivative of loss with respect to W, we are passing through time. That's why this algorithm is called back propagation through time, or BPTT, because this W is depends on previous time steps W, this W again depends on previous time steps W, and like this it will continue. And again, once you calculate for this one, similarly for this one also same rule, del LT3 by del W is equal to, similarly you calculate, there's two steps, here one step, and here directly you can calculate. So, and you add all, it will give you the final derivative. Similarly, for u also in the same manner you can calculate, because u also depends on time. Okay. So now once you get, you update the using your back gradient descent method, you update the w's, and the training will complete. You will get the final WUV, and that will be trained model. You pass any input, it will give you the output. Okay. Now, what is the benefit of using RNN? Okay, so the benefits are like this. So if you use RNN, there is also another counterpart is called hidden Markov model. It's a traditional approach. We have not discussed. The hidden Markov model also used to for sequence labeling, for sequence processing task. But just let's just consider neural network and plain neural network and RNN. So neural network cannot create a model, or it cannot model sequential information. Sequential it cannot process. As a whole, you give the some information and it can process. But sequentially, one after another information it cannot process, which can be done by the RNN, or recurrent neural network. Uh, Handling variable length input. Your RNN can handle variable length input because it is processing word by word. If a sentence has 5 words, so the time step will be 5. 5 times it will process. If the sentence contains 10 words, so there will be 10 time step. But such kind of thing cannot happen in plain neural network, because it is fixed, means it is fixed. You cannot change it further. Okay. Takes entire sequence into account when we are considering the RNN, because at last you will get the output. Okay. Every time you will get the output, but you may not consider that. Only last output you can consider. Where in plain feed forward neural network, that cannot be possible. So that is the benefit of using RNN. Okay. So this is your RNN. Let's discuss something called a language model, because language model is very important nowadays, and all these language models, large language model, based on this concept. Just understand this concept, then you can read the advanced materials to gain more knowledge about LLMs. So this is the foundation. What is language model? Let's say this is the sentence. She spent the day swimming in the dash. Now, this is a question that if some words of a sentence is given, can I find out what will be the next word, so that the sentence will be complete? So, can it be lake? Can it be ocean? Can it be milkshake? Can it be bleach? So, if you see, let's say there are only 4 possibilities. Out of these 4 possibilities, which possibility is more likely? That means it's kind of a probability calculation. Okay. So what we'll do? Language is predictable. Some sequences are more probable than others. So here, she spent the day swimming in the milkshake cannot be possible. Bleach cannot be possible. Either it can be a lake or a ocean. Okay. Now, why this is intuitive? Because language has a certain kind of structure. You can find out the probability of a next word given a sequence of previous word. We call this as a language model. Language model is nothing that to find out which word is most probable given the previous words. So that means it is predicting the next word, and your LLM is also doing that. It just predict the next word reading the previous word. Once previous word is there, based on the previous word, some model is there, some calculation is going on, and out of all possible vocabularies, which word is more probable, that is outputted. Okay, so that is called your language model. Now that means the language model determine the probability of a sequence of word. For example, out of these two, lake and ocean, which is more probable? Now you have to find out probability of lake given all previous words. Let's say it is 0.6, let's say, and probability of milkshake given all previous word, let's say it is 0.2. So obviously 0.6 is greater than 0.2, so the next word is lake. This is the job of the language model, to predict the next word. Okay, and formally you can calculate using this formula, that is probability of wi given all previous words, which is nothing but probability of w1, probability of w2 given w1, probability of w3 given w2 w1, or like this. And you can use Markov property to shorten the probability calculation and find out the final probability. That we are not going to discuss. But remember, language model is nothing to find out the next, which is the probable next word given some previous words. Okay, so the language model can determine the probability of a sequence of words, which can be used in speech recognition, translation, autocorrect and completion, text generation, and in many more applications. Nowadays everybody is using these language models. Okay, now the question is how we can use a RNN to produce some of the outputs as a language model, how we can use. Okay, so let's see. That means we have a corpus, we segment them into sentences or paragraphs or chunks or documents. Okay, and now these are given as input one by one to the RNN. Let's say at time step 1 I am giving C as the input, and previous hidden state is 0 vector. Now it is producing some output. Now let's say I have a vocabulary. Okay, so what we are discussing, that how RNN can be used as a language model. So what we will do at the time step T1, we are giving input. Let's say first word is C. C is given as input. Now there is a vocabulary list for my problem. Let's say the vocabulary list contains 100 words. Out of 100 words, what will be the probable words? Okay, okay. Let me share it again. Okay. So what I'm saying, that when C is given as input at time step t equal to 1, it produces some output. Output how it is producing, because there are many possible words. It will calculate the softmax probability. The probabilities are there, but it says that heat is the maximum probability. That means the next word must be heat, but actually the next word is swam. So what we'll do, we'll use swam as the output, means actual output, and the output here is zero point 0.6, that is heat. So we'll calculate the loss using swam. Okay, now this is called the CC loss. Now what we'll do, now this one is given as input, actual output is given as input here. Okay, again it will produce some output. Now we'll calculate the probability, sorry, the loss with respect to in, and this process will continue, and overall loss. So here, when we do this, what it is trying to do, after each time step, it is trying to produce the correct next word. Okay, so this is nothing but how RNN can be used as a language model. For example, let's see here C swarm at time step T3 at H T2, C swarm already it is produced or it is there, and I want to produce what will be the next word. Actually the next word is in, but when you give this, it will give sir, actually the next word is in, so it should be produced in. So now if it is not producing in, it will produce some other word. You will calculate the loss, and this actually the in will be given as input, not the this one which is produced, and it will produce another output. And this each time step, this can be viewed as a classification task. At each time step it will try to predict out of all possible words what will be the next word. So this is nothing but the language model representation using RNN. Okay. So your input is in, hidden state is C, so far is C swarm. So output is the probability of each word in the vocabulary being the next, what we have discussed. And this kind of training is called teacher forcing. Remember, what is teacher forcing? Very simple. Teacher forcing is, instead of giving the output at a current time step to the or predicted output at the current time step to the as input to the next time step, we are providing the actual output of the current time step as the input to the next time step. That is called the teacher forcing. Okay. So how text is generated? Let's say a start token is given as input at time step T1. Then the previous hidden state is 000, means zero vector. It produces some output. Okay, whatever output it is producing, it will be checked against the actual output, and loss will be calculated. In the next time, let's say it is sampling the. Now in the next time step, this the is given as input. Okay, the is given as input. Once it is you see, once it is produced, the is given as input, and again it will produce some output. Let's say cat. Again cat is given as input to the next time step. It is producing knocked. Knocked is given as input to the next time step. Over is output. Over is given as input, and the is output. So this kind of processing or text generation is called auto-regressive generation. Means whatever output is produced at the time step, at the current time step, that will be input to the next time step. If you are doing this, this is called auto-regressive generation. During training, if you are not providing the predicted output as input to the next time step, rather you are providing the actual output in the next time step, that is called teacher forcing. Just remember these two differences. Okay. So question is, once a language model is created, how will you evaluate it? Because precision recall is not the actual metric to evaluate. Many metrics are there. One very famous metric is called perplexity. What is perplexity? Now this is the inverse probability of the test set. You have a test set, you calculate in probability of the test set, take the inverse and normalize it with t, means number of words present, and that whatever value will come, that is called the perplexity for that language model. And if the perplexity is small or lower, then it is better. Okay, because as it is inversely proportional. So perplexity is the metric used to evaluate whether a language model is good or bad. If the perplexity score is less, then it is better. If perplexity score is more, then it is not better. Okay, you remember this much. Now another concept with this RNN is called long range dependency. Let's see how long range dependency is actually affecting our output in the RNN. For example, let's see, this is the sentence. He was supposed to meet his friends at the show, but something came up at work, so he called dash to say he would be late. Now question is, what will be this dash? So as a person, when you read it, this dash is nothing but the friends. So for the friends, what we are writing, we can write them. That means this them is dependent on these friends. So you see, the word them is dependent on a word which is far from here. We call this as long range dependencies. Okay, so your them is dependent on friends. Now why it is a problem? Now what happens in our RNN? In RNN, At time step T1, whatever information is there, it is captured. Means this input is captured here. Now this input, this information is passed to the next time step, and current input is this one, xt equal to 2. Let's say this is yellow. Now this one, previous information and next information is combined. Now at the next time step, this previous two information and current information is combined, and at the next time step, previous three information and this information is combined. So that means at each time step, we are just combining the previous information which is passed through this recurrence and the current information. And generally the current information share is more than all the previous. So when it goes on and on, you see this red strip is decreasing. Means the dependency, if there is some word, let's say this word is dependent on this word, then as this information is very less here, so the dependency cannot be captured. Okay, so that means earlier signals is weaken over time because it is morphed. We are overwriting again and again and again. If the sequence is very long, at some time this red is not there. Very small information of the first word will be available. So that creates a problem. We call this as long range dependency problem. Okay, and when you do the back propagation, as the information is very less, so when you calculate the gradient will be nearly equal to 0. So when it is nearly, because it is repeated multiplication, you just go on multiplying here in this long range. So as it is repeated multiplication, as the initial value is very small, when you go on multiplying, it will be nearly equal to 0. When it is nearly equal to 0, it is called vanishing. Gradient will vanish. If gradient is vanishing, then the updation will not happen. Means the previous input or the previous weight will be equal to the next weight. So the updation will not happen, means it is not learning anything. So this is the main problem in RNN if the sequence is very long. Okay, so to solve this problem, what we have to do? We have to use different architecture. So a simple RNN often has a hard time modeling long range dependencies. Few remedies are there: batch normalization, careful weight initialization, gradient clipping. These are the short-term relief. But we need to create a different cell structure or cell architecture to solve this long range or vanishing gradient problem. Okay, and that is called LSTM, long short term memory. Okay, so let's quickly go through it. What is long short term memory? So only difference with RNN and LSTM is that this cell, now inside this cell in RNN it is only one single layer, hidden layer, but here we can change this cell or hidden state, a hidden unit into different architecture, and that will have some gates which can remember important information from past. Okay, and discard unimportant information, so that what will happen, now this dependency problem can be solved. Let's see. So here each cell contains gates which are nothing but same neural network layers which will control information flow. That means which information is required, which information is not required to flow in the time, that will be decided by these gates. So in general, there are three gates available within a LSTM cell. Let's see. Let's say this is your LSTM cell. Now, what is the input to this LSTM cell? It is your previous hidden states output and current input. Xt is current input at time step t, and previous hidden states output. There is another input is there, that is called cell state. So the cell state is actually the memory. It's like a conveyor belt passing through all cells through time, and it contains all information. Whatever information you need to store, you need to store in ct-1, and it will pass through all the cells. Now initially what will happen, now this ht-1 and xt will be given as input to a gate called forget gate. So this forget gate is using a sigmoid activation function. What it will do? It will calculate a mask, a probability mask, which will say that how much information from this cell state will be passed and will be forgotten. Okay, so what it will do? So your input to and output from gate, that is your sigmoid or vectors. This is passed through a sigmoid function. It will give you value between 0 and 1. 0 and 1 means it will act like a mask. Okay, and this mask acts as a mask to remove information from city manager. Now this one is multiplied done a dot product or element wise multiplication with this one. So what will happen if some portion some probability, if those probability which is 1, it will contain everything. If the probability is 0.6 or 0.9, that means 0.90% information will be passed through, 10% will be thrown away. So this will control, this forget gate will control how much information from the previous cell state to pass through this current cell state. Okay. Now this is the job of forget gate. How much to forget, how much to pass. Okay. Now there is another gate called input gate. Input gates in the same you can calculate, that is UIXT, WIST minus 1. Input gate's job, it creates also a mask. It will determine which new information from these input need to be passed to this cell state. So for that we have to calculate new information using this C tilde, that is tan H UCXT plus WCHT minus 1, that is XT and ST minus 1 is being used with the tan H activation. So it will calculate the new information. Now from this new information, how much you need to add in the cell state, that will be decided by this input gate. So how will you calculate? You just do a similarly element wise multiplication, and that will be added here with this cell state. Now your final cell state is ft dot ct minus 1. This ft dot ct minus 1, when we do this, it will forget some information, pass only required information, plus this new information which you have calculated with it and dot c tilde. This new information is added with this. So now you got ct. So the forget gate will decide how much you need to forget, what to pass. The input gate will decide how much new information will be added to the cell state. Now there is another gate that is called output gate. Now this city is updated here. Now from this city, from this information, what need to be output at the time step t, that will be decided by the output gate. So here is also a probability mask. Now what it will do, you just find out the tan H, just apply the tan H with the city, the current cell state, and this just do the output gate, just do the multiplication, pointwise multiplication. Now you got the HT. That HT is OT, pointwise multiplication with the tan H of CT. So this output gate will decide how much from the cell state, updated cell state, to be given as output. So one HT is here, that is output to the next time step, and this one output at the current time step. This is the output, and the cell state is passing, and this is called your LSTM cell. Now these are the different weights. So you see, for forget gate, 2 set of weights, for input gate, 2 sets of weight, for new cell information, 2 sets of weight, and for output gate, 2 sets of weight. So these are, there are 8 sets, means total 4 sets of weights. Okay. So this is your LSTM. Now there are different architecture of RNN. RNN can be simple RNN or RNN can be LSTM. There is also another version of this RNN. We call it a GRU, gated recurrent unit. Similar to, it is similar to your LSTM. Now there are stacked RNN. Stacked RNN means it's one architecture. You can stack multiple RNNs one after another like this. This can be done. Means at time step T1, this is one cell. Again, the output will be given to another cell. Again, output will be given to another cell, and final output will be given as output. So this is called stacked RNN. Okay. Similarly, there is a bidirectional RNN. Bidirectional RNN, why we need? So bidirectional RNN is required because sometimes when we process the output, we are processing an RNN from left to right, and if you are in the cell state, if you are in the time step t equal to 3, you are only considering the previous 2 words. You are not considering the next word because yet you have not gone there. But sometimes you need to consider the next words in order to correctly classify this time step T3. That is YT3 cap. Now what you will do? Now for that you need another RNN which will move from right to left. And why it is required? It is generally required in part of speech tagging. Let's see. Brown refused to testify. One sentence. brown sofas are on sale. So you see, if you categorically see here, brown is a noun because brown name of a person. But here brown sofa means brown is adjective. Now you do not know these three words or these three or four words after brown, you cannot correctly classify whether it is a noun or whether it is an adjective. Means if you do not know these things, so you cannot correctly class. That means you need to process from right hand side also. So to do that, what we'll add another RNN layer which will pass from right to left. Okay, so right word will be given as input, then next word, then next word, like this, and both will be combined as the output YT cap. This kind of architecture is called bidirectional RNN. Okay, so this much I have to complete. So what we have completed here, what is RNN, how RNN is processed, how means what is language model, how RNN is being used as a language model to generate text, and what is LSTM, and different types of architecture of RNN like stacked RNN and bidirectional RNN. Is it okay? Is there any doubt? Okay. So let's do some hands-on on whatever we have discussed. RNN. Is it visible?
Yes, sure.
Okay. So let's see. Okay. So to run this notebook, you need to change the runtime. So how to change the runtime? You just go here, click change runtime, type. There is a free GPU available, T4 GPU for 1 or 2 hours. So you can select it and save it. So the runtime will be changed because these are means highly sensitive, means high performance computing is required. So we need some kind of GPU. So GPU is free for some time in this collab. So we are going to use that. Okay. So first thing first. So what we are going to do? We are going to create a part of speech tagging. So using RNN. So that means we'll provide a sentence. For every word of that sentence, one part of speech tag will be the output. Okay, so this is our problem, and how that can be solved using RNN. Let's do it. So these are the libraries that need to be imported. So just import them. NLTK, NP. One is request. Request is to download something from the internet, and the model checkpoint you will see. So these are the um, libraries that need to be downloaded. Okay. Now for creating a part of speech tagging solution, we need a data set. And there are already available some data sets, so we are going to use that. So three data sets are available. One is in the NLTK, one is called Tree Bank, Brown, and Cornell 2000. So these data set contains what? The data set contains the sentence, in one line, one sentence, and for that sentence, whatever words is there, for each word, corresponding part of speech tag is also there in the output. Means there are two columns. Okay, so let's download them. So we have downloaded this Tree Bank, Brown, and Colonel 2000. And one problem with these three data set, as we are going to use the three data set combinedly, one problem is that they have their own type of part of speech tag. Sometimes some contains noun, some contains different types of noun. So different part of speech tags are there. So to make them into one part of speech, there is a universal tag set present in NLTK. Let's download it and apply that universal tag set to all these three corporas. Okay, so to do that, what we are doing now, first just download all POS tags, treebank.tagged sentence, just universal, apply universal tag set for all these three downloaded data set, we are applying universal tag set. So just apply that. And if you want to see one element of that data set, let's see what it contains. It contains like this. This is one sentence. For that sentence, we have the list of sentences, and in each list there is a tuple, different tuples. Each tuple contains the word and its corresponding part of speech. Means the sentence is Perry Winken 61 years old. This is the sentence we will join, and their corresponding part of speech is Perry is noun, Winken is noun, dot is dot, 61 is number, years is noun, and like this. Okay, so this is my data set. So first thing first, what we'll do, we have to segregate, because we need to create one list of data set contains sentences, another list of sentences contains part of speech. So for that, what we have done, we have created two lists, empty list. One is sentence, one is sequence tag, and just pass through this for loop. So what it will do, it will create two sets, two lists. One list contain the sentences, and their corresponding tag set is contained in sentence underscore tag. Now if you want to see, you see here sentence 0 contains the sentence Pierre Wenken's 61 years old, like this, and sentence tag 0 contains their corresponding tags. So we got this. Okay, and how many such sentence and tag pairs are there? There are 72,202 sentences, and their tag sets are there. Okay, now what we'll do, now your data set is there, we need to convert them or split them into training, testing, and validation. So here train ratio is 75%, validation is 15%, test ratio is 10. So there are two times I am applying train test split. First time in the whole data set, when I apply, it creates train and a test. Now on the test set, I am applying again to create the test set is divided into again another two part. One is test, another one is validation. Okay, so just run it. Now you have what? You have three things: X train, Y train, X val, Y val, and X test, Y test. The whole data set is converted into three sets. The training set contains 54,000 sentence and their corresponding tags, and the validation set contains 10,000 and their tag, and the test contains 7,000 and their tags. Okay, you have these three. Now, first thing what we'll do, because these are words, they cannot be processed by any neural network. RNN is itself a neural network. So we need to vectorize them, and we know how to vectorize them. So there is a, we will not use any sophisticated vectorizer, rather we will directly use Keras pre-processed tokenizer to vectorize it. First you need to tokenize it. So apply tokenizer, yeah, and if the word is not available, use OOV. So you just apply this tokenizer and fit it on training data. Okay, and if you want to see how many vocabulary size, what is the vocabulary size, it is 52,000. Okay, similarly you apply the tokenizer on the tests, sorry, on the training set also, because the training set is also not number. The training, sorry, the Y train is not a number, rather it is a tag set. Tag set means again it is sentences. So we need to convert them also into tokenizer. So if you see how many tokenizer is there for Y train, only 12, because there are 12 tags. Okay, what are their indexes? If you want to see, so these are the indexes. There are 12 tags and their index is there. That means when you vectorize them, these index will be used. Okay. Now convert them into vector form, that is text to sequence. So text will be converted into their corresponding index in the vocabulary which you have created using tokenizer. Now this is done. Now if you want to see what is the sequence 0, so these are the indexes for this first sentence. Okay, and if you want to see its original form, this is the original sentence and this is the reconstructed sentence. Okay, now what we have to do, we have to apply the same thing on Y train also. Means Y train is need to be converted into their corresponding sequences. So text to sequence is applied here. So here these are the text to sequence, determiner, verb, etc. Okay, and same processing, means tokenization and convert to vectorization using indexes for validation data also need to be done. Now your training data, X train, Y train is converted into vector with indexes, and your validation data also x val and y val is also converted into vectors. Okay. Now, what we'll know? What we'll do here in RNN, variable length sentence can process, that we have seen. But for simplicity, as we are going to process batch by batch, but in each batch, the sentence length must be same. So to avoid recreating batches and then change the sentence length into uniform, instead of doing that, what we'll do, we'll pad everything with maximum length so that every sentence will have same length. Then we will batch it and we will feed it to the neural network. For that, first we have to find out what is the maximum sequence length in the total data set. That is given by max length, it is 161. So what we'll do, we'll pad them. Okay, so just extend, just pad it with the post padding. So this is the post padding, means every sentence, if you see the first zero, every sentence is padded with 160. Total number of token must be 161, and some of the tokens are not there, it will be zero. Okay, like we have already done in the last session. Similarly, you also do it for Y train also, because also Y train need to be padded. And also that will be done for the validation set also. Training set and validation set padding is done. Now, as the output, here output is a multi-class classification problem, because out of 12 tags, one tag will be the output. And to use multi-class classification problem, we have to convert the output into one-hot vector. Already we have seen. So that need to be converted. So Y train padded must be converted to one-hot vector. To do that, Keras has a two categorical function. Just call it pass Y train padded. So it will be converted into one-hot vector. If you see, this is the one-hot vector. And if you see the first element one-hot vector, this is the first element. Okay. Similarly, if you want to find out a tag set for a given index, that can also be done using index to word function. Okay. Now the validation data is also need to be converted. Means y val is also need to be converted into one auto vector using categorical. So y train and y val are converted into vectors, one auto vectors. Now it is ready to create what your model. Now to create a model, we have to find out what will be the number of tokens. Let's say I am, so the number of tokens is nothing but the number of words present. Okay, so your number of words will start with, if you using word index, it will start with 0. So we are adding 1. And the embedding dimension, we are taking 121, you can change it also. Okay, and number of classes is 12. Because how will you get that? Now word index for tag tokenizer, it will give you 11 plus 1 is 12. So now this is the case. Now how to create a model? So again we have to use the sequential API, same sequential API. First layer is embedding. Here you have to see some of the important things that is different from the previous embedding layer. Now in the embedding layer, input, output, input length, both are same. But here mask 0 is given as a true. Why mask 0 is true and what is its use? So mask 0, it will say that when you make it true, it will discard in the further down the stream when it is going to process, it will discard those padding sequences to find out their output, because we only need output for the data which is available. And when we are adding zeros for the padding, for them there should be no output. There should be no output. So what we'll do? So to discard that automatically, the mask 0 is being used as a true. Okay, this is one change. Now to create RNN layer, here we have used LSTM. So LSTM is an improved version of RNN. So just very simple. Just call layers.lstm. Pass how many units are there. Well, let's say I'm passing 128 units. And here I'm writing return sequence equal to true. If you write return sequence equal to true, that means at every time step, it will provide one output. But if it is a classification problem, I need only final time steps output. So in that case, you have to do return sequence equal to false. Okay. So this is LSTM, but rather than using simple LSTM, I am using a bidirectional LSTM. So you just call layers.bidirectional and wrap it with LSTM. So LSTM is wrapped inside the bidirectional. So it will become bidirectional LSTM. Okay, and after that you add a dense layer. So the dense layer is used for finding the output. And here I am using softmax because it's a multi-class classification problem, because there are 12 classes. Out of 12 classes, one class will be the output. Now your model is ready. Very simple model: one embedding layer, one bidirectional LSTM layer, and final output layer, that is the dense layer. Now you compile it using categorical cross entropy, because it is a multi-class classification problem. So it is categorical cross entropy. Optimizer is Adam, metric is accuracy. So compile the model. Now the model is compiled. Now you have to train it. So if you want to see the summary, this is the summary: one embedding layer, one bidirectional LSTM layer, one dense layer. Okay. Now here I have created a early stopping callback. It monitors validation loss, patience equal to 3. That means up to 3 epochs it will check whether it is increasing or not. If for continuously 3 epochs the validation loss is increasing, not decreasing, so it will stop. Okay, so that callback I have created, and for training we call model.fit. X train and Y train is passed, epoch is 20. Here batch size is 256. I mean, at a time 256 data will be loaded in the memory. So validation data is passed to create the validation, to calculate the validation loss and accuracy. So when you train it, you will see after certain epochs, it will be when the validation loss is decreasing, so it will be stopped. So this is one kind of regularization already we have discussed. So let's see. So this is the epoch 1. So at the end of epoch 1, you see the accuracy is only 78%. Training accuracy. Validation accuracy is 95. But at epoch 2, training accuracy is 96, validation accuracy is 96, means increasing. And in epoch 3 is 97, it is 96. Now it is decreasing. Here it is 98 and 96. Again it is decreasing. Here it is 98 and 97. Little bit increasing. So if for continuously 3 epochs, if it is decreasing, then it will stop. Now again it is 96. Again decreasing. So 97. So now it is stopped. So you see my training accuracy is 98, validation accuracy 97. Means now it is a good model. So now what we'll do, we have to test it. So there is a test set already there. So we have to again tokenize the test set and pad the test set, then tokenize the test output, means your Y, and pad them and convert them into categorical. These three things has done here. Now you call the evaluate function on the model, pass the X test padded and Y test categorical. Now you see at the test set, the accuracy is 97%. Loss is only 0.10. Okay. Now your model is ready. This is the LSTM, bidirectional LSTM model, which will be trained on a data set of a PO stack. Now to check whether it is working or not, let's say I have two sentences. The sentences which we have used in the presentation: Brown refused to testify, brown sofa are on sale. Let's see whether it is correctly classifying this brown or not. Okay, so for that, what I have done, I have created a function which will infer or output the given input. So what I have done here, the sentence is given as input, it will be tokenized, then it will be padded, because already whatever pre-processing activity you have performed on the training, the same pre-processing must be done for the new sentences. So you have tokenized, then you have padded, okay, then you predict. So when you predict, it will give you some target predictions, because there are 20 predictions for every sentence. So that prediction will be used to find out which is argmax, means use argmax to find out which tag has maximum probability. That will be the output. So this is the function. Now you just pass here. Now I am calling tag sentence samples. Just pass this. So what happens? Oh, this one I have not run. Okay, now you see. Now this is done. Now let's print the output. If you print the output, first one, now brown is noun. If it is second one, now here brown is adjective. Brown is noun, refused is verb, to is preposition, PRT, testify is verb. Here brown sofa are on sale. So here brown is adjective, correctly classified. Sofa is noun, are is verb, on is adverb, and sale is noun. So on is adjective. What is on? ADP, adverb or something. Okay. So now correctly it is classified. Okay. So this is your what part of speech tagging means one-to-one classification. How it is being done. And I'm not saying how language model will be used. So here also another language, how we can create a language model is there. You just go through it. It's same what I have done here. Here we don't need to create any training testing split. Rather we downloaded a text, means a whole text. Okay, now that text need to be converted because we are going to create a language model which will predict not the word, rather character. What will be the next character? Okay, so in the same manner you can use the word. So you do the tokenizer, fit on that tokenizer. Okay, then what you do, these are the tokenizer. The next thing is that you need to convert these sequence of tokens for the particular test into slices, tensor slices, so that we can create a data set out of this total paragraph or total document. So tensor slices has been applied. It create a different slice. Now on that slice, what you do, just I'm telling you that you, let's say you slice it between all the total paragraph, whatever it is containing, it slice into 101 words. Each slice will contain 101 words. Now when first slice is created, the next slice will be created from the next one. You see here, first slice is created from 27. Next is 21, one like this. Next slice will be created from 21. Means it's kind of window which is shifting towards one by one word. And then next slice is created from one, because this is one. Next slice will be created from 8, like this. So all the document is sliced into number of sequences. Okay. Now that will be used as input and output. This one will become input, then next one will become output. Okay. So here you just create that map, convert them into tensors. Okay, I'm just quickly going through it. Everything is written. You can easily understand once you understand the LSTM. Now what I have done here, once it is converted into, then it is converted into batches, because batch by batch it is going to be processed. And each batch is like this, just to show what it contains. Now for each batch, the data set, the preface is not good. Now the model is created here. You see here LSTM, we are not using bidirectional LSTM because it is going to produce one after another character. So the two LSTM layers has been used, one dense layer is used, activation softmax. Why? Because out of all characters, possible characters, one character will be the output. So there are only 56 or perhaps 56 characters are there. So when once one character is there, next character will be predicted out of the 56. Again, two character is there, next character will be predicted out of the 56. And this is a prediction, simple multi-class classification problem. So that we have used softmax. When you train it, because the training takes more time. Okay, so when you train it, you will create a model, and that model can be used when you give. You see, just I'm going to the last one. When you give this input, let's say I'm putting banana peels are battlefield can. Okay, number of character, next number of character to be generated is 300. Your temperature means how much you have sampled. If temperature is low, then the sample character will be more accurate. If temperature is high, it is more random. Okay, just to remember that part. And when you put it, it generates 300, next 300 characters like this. Banana peels on the battlefield can over the apples and the abroad, and men will drop down exhausted. So somehow it is producing good result. When you increase the temperature to 2, you see it's not that much informative. To know a command bgin to see a camp razari. So when you increase the temperature, it is more flattened and more random. But if you decrease the temperature, it is more accurate. Okay, so this is called a character level. So if you want to do further exploration, some of the pointers are given, you can go through it. Okay, any doubt? So just go through this language model part, because I am quickly cover it. Everything is written easily, you can understand. Okay, is there any doubt, anyone? So we have almost covered everything. Okay, starting from simple NLP task to advanced NLP task using RNN and LSTM. And if we can take another class, then we can go for attention. Otherwise, this much is sufficient to create any kind of NLP, to solve any kind of NLP task. Okay, any question?
No answer. Tomorrow we have class, or directly we'll take the break, and after 15th only we'll take the class, because they
So
are
actually,
supposed
sir,
to.
I have to only one thing to cover, that is attention,
Okay.
RNN with attention.
So do you
So
want to
and in
take class
that also
tomorrow?
we'll discuss encoder decoder part, so that they can create translation tasks.
Okay.
So
Do
one
you
thing is
want to
there,
take
so
class
that
tomorrow?
we can cover also in the 15 after Raja vacation.
Okay, fine. Then all of you, the students, those who are joining, so you just attend all the sessions of the workshop, NLP workshop. Fine. So where the main theme is your low resource NLP. So how in low resource languages you have to implement all these things. That is your challenges, and all the resource persons are very experienced, and they are going to tell about their work. Okay, and definitely Hansen will be there. So from there we can take some problem statements. So along with the answer, we are trying to solve all those things for the next 15 days. Like after this auto encoder part, we are going to implement the projects only. That means the many problem statements we have to solve. Okay, so these 30 to 35 friends are joining. So our focus is also to you only, and if somebody is joining outside, means in the workshop directly, we'll also ask them to do the mini project,
Project.
and that
Yes.
project will take forward to the this either to the journal paper or patent, like that. So I have a plan. We are going to all these 30 students. I will take the one session in between 15. Means after 11th only I will take one session. So where I will tell you to complete four tags. That your first one is your invention disclosure. So where 13 points are there, I have to discuss all these 13 points, how we are going to write, what is the architecture, why, how your idea is unique. Okay, if any alternate solutions are there, I will tell you all the 13 points. So you have to write down 4 to 5 pages. Those invention, this disclosure, we are going to apply for the patent. Fine, that is one thing. Second one is your, I'll show you 3 to 4 projects. So accordingly, you have to write down the research proposals. So if somebody, many of you wants to go for the MS or MTech, so their research proposals are required. So we want that you just write down the research proposal, so that we can modify those research proposals, and we are going to apply. Mr. Nayan sir is going to apply in his university some projects. I'm going to modify those things and I'll apply in my university. So if project will, if in any case we are going to get the projects, so definitely those students, those who have written that particular research proposal, we are going to give you preference to continue in that project. Okay, definitely stipend will be there. Okay, that thing later. The second thing. Third one is your systematic review. So whenever you are going to start any problem statement, we have to do one systematic review to evaluate what are the works has already been done in that particular area. Okay, what is the loophole there, what the pros cons are there, and we are going to do those things. Nowadays, ChatGPT is there, easily you can find out. But we have to do the tags by using some tools. Some Probus tool is there, Ovin tools is there. So either me or one of my student, I'll ask her to explain you how you are going for the systematic review, which is also going to be published in the journal paper or something or something like that. And after that, same problem statement will take forward to the journal paper. Okay, we'll do more experiment like whatever things that sir is covering, RNN or auto encoder model or bot model or robot model in the low research languages. After implementing those things, how we are going to write down the journal paper. So samples is going to be discussed and you have to do that one. So after that only, and the internship certificate is going to be provided to you. Okay. Those who want to continue, suppose 2 months internship is there. So if the tax required 3 months, so definitely we'll get the certificate for the 3 months, 3 month internship. So in 2 months, those who want to quit or those who are not attending, I can give the certificate in 2 months, no problem. Without any publication, without any patent, without any like that systematic review, you can take the certificate. If you want, you are going to continue with us for the next 1 or 2 months, 3 months or 4 months. So definitely try to finish all these tags, take the certificate of 4 months or 3 months, and that will be helpful for you because one publication will be there with you. Okay. So this is from my side. Yes, Nayan sir, you want to say something?
I want to say that whatever we have discussed means particularly last 2 3 sessions, that is very important. And only one session I need to make to understand what how attention is being used in this RNN, so that you can apply this on your transformer to understand the transformer, as well as you can apply this on translation tasks. That only one class I need to take. So I think I will take after the break. And during this time, you just try to execute these problems. Means just whatever notebook I have shared, just try to understand it. If you are unable to understand anything, everything is written. Easily you can understand. If anything unable to understand, then you can also talk to me. No problem.
And you can
And
interact in
also,
WhatsApp also. If any problem you
yes,
are
yes, you can
facing, then you can interact with WhatsApp. No?
ask questions on WhatsApp. I will try to answer it. No problem.
Okay, so on 6th of June, we are going to meet at 10 o'clock or 9:30 in an innovation session, followed by
Yes.
15 sessions will be there from 6 to 10. Okay, so try to attend at least these 30 to 35 and at least attend all the sessions, try to attend all the sessions so that we can interact with the resource person as well as you will get the problem statement on which you are supposed to write down the pattern, systematic review and journal papers. Okay, so is it clear to all? So try to attend all the sessions. Anyone is attending or not, forget about that one, you just attend. Fine. So thank you very much. So I will upload these records,
Thank you, sir.
all the recordings. Fine. Thank you.
Thank you, sir.